In this episode, we are going to focus on model validation, which is the moment you stop trusting hope and start trusting evidence. For brand new learners, it can be tempting to believe that if a model produces impressive outputs in a demo, it must be ready, but demos are often designed to show best-case behavior. Real users bring messy inputs, unpredictable context, and pressure to rely on outputs in ways the designers did not intend. Model validation is the discipline of proving, before and after deployment, that the system performs well enough, stays stable under stress, and generalizes beyond the exact examples it learned from. The title gives us 3 pillars to build on: performance, robustness, and generalization testing. Performance is about how well the model does the job it claims to do. Robustness is about how it behaves when inputs are unusual or adversarial. And generalization is about whether it can handle new situations that are similar but not identical to its training experience. This matters in Domain 3 because validation is what connects data and lifecycle discipline to real outcomes, and it is one of the strongest controls you can have. By the end, you should understand what validation tries to prove and why each pillar protects you from a different kind of failure. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Let's begin by defining validation in plain language, because beginners sometimes confuse validation with training. Training is the process of learning from data, while validation is the process of checking whether that learning produced behavior you can trust. Validation asks questions like, does the model meet the requirements for the use case? Does it fail safely? And does it behave consistently across the contexts it will face? Validation is not only a technical activity, it is also a risk activity because it informs whether the system is safe to deploy and how it should be constrained. A key beginner idea is that validation is only meaningful when it reflects the real use case. If you validate on easy examples, you will be surprised in production, and the surprise will look like the model suddenly got worse when in reality your validation was too narrow. Validation also must be tied to the specific version of the model and its configuration, because changes in data, settings, or environment can alter behavior. Another important point is that validation is a process, not a single number. People often want a single score that says safe or not safe, but real validation is a body of evidence that supports a decision. When you understand validation this way, you can see why it is central to responsible AI risk management. Performance is the first pillar, and it is about whether the model does what it is supposed to do with acceptable quality. Performance depends on the task, but the deeper idea is that you must define what good means. If the model summarizes documents, performance might mean the summary captures key points without inventing facts or omitting critical details. If the model classifies messages, performance might mean it assigns categories correctly enough to support the workflow without creating harmful misroutes. If the model generates text, performance might include usefulness and coherence, but it also must include correctness for factual claims when facts matter. A beginner trap is confusing fluency with performance, because fluent language can make wrong content feel right. Another performance trap is relying on average performance, because an average can hide severe failure for certain groups or situations. This is where fairness and representation concepts connect to validation, because performance should be examined across meaningful segments. Performance testing is therefore about measuring quality in a way that matches the purpose and the risk. When performance is defined carefully, the rest of validation becomes clearer because you know what you are trying to prove. Robustness is the second pillar, and it is about whether the model keeps behaving reasonably when conditions are less than ideal. Real inputs are often noisy, incomplete, ambiguous, and sometimes intentionally manipulative. Robustness testing explores what happens when spelling errors occur, when inputs are short or oddly formatted, when context is missing, or when users try to trick the system. Robustness is not about making a model perfect. It is about understanding how it breaks and ensuring it does not break in dangerous ways. For example, if a model produces a recommendation, robustness includes checking whether it becomes overly confident when it should be uncertain. If a model provides summaries, Robustness includes checking whether it invents details to fill gaps when the source is unclear. Another robustness concern is sensitivity, meaning whether small changes in input cause large changes in output, which can indicate instability. Beginners should remember that robustness is about the edges of behavior, not the center. The center is what you see in polished demos, but the edges are where users get hurt and where incidents begin. Robustness testing is a way of finding those edges before the system reaches the public. Generalization is the third pillar, and it is about whether the model can handle new situations that are similar to what it learned but not identical. This matters because the real world changes, and because no training set can include every possible case. If a model only performs well on examples that look like training data, it may fail as soon as language changes, new products are introduced, or user behavior shifts. Generalization testing looks for whether the model learned the underlying concept or simply memorized patterns. A beginner-friendly way to think about this is to imagine a student who can solve practice problems they have seen before but fails on a new problem that requires the same idea. Good generalization means the model can apply knowledge flexibly, while poor generalization means it is brittle. Generalization testing often includes evaluating on new data collected from realistic contexts and checking performance across different conditions. It also includes checking how the model behaves when it encounters rare or emerging scenarios that were not present during training. If generalization is weak, the model may appear strong in development and then silently degrade in production. That is why generalization is a risk control, not just a quality concern. These three pillars work together because they cover different kinds of failure that can hurt people and organizations. Performance failures are the obvious ones, where the model is simply wrong too often for the task. Robustness failures are the sneaky ones, where the model is fine in normal conditions but unsafe or unstable when inputs are messy or adversarial. Generalization failures are the slow ones, where the model looks good initially but does not hold up as conditions change. Beginners sometimes assume that if you improve performance, you automatically improve robustness and generalization, but that is not always true. You can over-optimize for performance on a narrow dataset and make generalization worse, because the model becomes specialized in ways that do not transfer. You can also harden robustness in a way that makes outputs less useful, because the model becomes overly cautious. This is why validation is not a single test. It is a balanced evaluation that informs trade-offs. The goal is to understand the system's strengths and limits, then design deployment and guardrails around those limits. Validation is how you turn uncertainty into managed risk. Another important part of establishing validation is defining the acceptable threshold for use, which is not only a technical decision but also a governance decision. What counts as good enough depends on the impact of mistakes. If the model is used for low-stakes drafting assistance, you may tolerate more errors as long as users are trained to verify. If the model influences higher-impact decisions, you need stricter requirements and stronger oversight. This is where human factors matter, because if users are likely to overtrust the system, then even moderate error rates can create serious harm. A beginner-friendly way to view thresholds is to connect them to consequences. If an error would be embarrassing but reversible, that is different from an error that could expose sensitive data or cause physical harm. Validation should therefore include risk context, not just raw scores. Establishing validation means agreeing on what evidence is required and what the decision criteria are before you run the tests, because otherwise teams can move the goalposts after seeing results. When criteria are defined up front, validation becomes a trustworthy basis for decisions. It is also important to understand that validation does not end at deployment, because models operate in changing environments. Post-deployment validation is sometimes called continuous validation, and it overlaps with monitoring, because you want to detect when performance, robustness, or generalization starts to slip. If the data distribution changes, performance might degrade. If attackers learn how to manipulate inputs, robustness might be challenged. If new scenarios appear, generalization might fail in ways not seen before. Establishing validation, therefore, includes planning how you will revalidate after updates and how you will respond to signals of degradation. Beginners sometimes think validation is a gate that you pass once, but for AI systems, validation is more like a repeated health check. This does not mean constant disruption. It means plan checkpoints tied to meaningful change events. For example, a major model update should trigger revalidation, and significant expansion of use cases should trigger revalidation. Without this discipline, the system can drift out of validated conditions while everyone continues to assume it is safe. A misconception that deserves attention is the idea that validation can prove a model is safe in all situations. Validation reduces uncertainty, but it cannot eliminate uncertainty because the world is too complex. The point of validation is to understand where the model is strong, where it is weak, and how to manage those weaknesses through design and oversight. Another misconception is that validation is only a technical team's job, when in reality product and governance must be involved because they define what success means and what mistakes are tolerable. Another misconception is that adding more tests automatically creates safety, when in reality tests must be relevant and meaningful. If you test the wrong things, you get false confidence. Beginners should take away that validation is a careful selection of evidence, not a random collection of numbers. Good validation makes limitations visible and encourages responsible use, while bad validation hides limitations and encourages overtrust. The quality of validation is therefore part of risk management itself. As we close, establishing model validation is about building evidence that the system's behavior is good enough, stable enough, and flexible enough for its intended use. Performance testing checks whether the model meets task requirements. Robustness testing checks whether it behaves safely under messy or adversarial conditions, and generalization testing checks whether it can handle new but related situations without collapsing. These pillars matter because they prevent 3 different kinds of failure: obvious failure, edge case failure, and gradual drift failure. Validation is most powerful when it is tied to the real use case, when thresholds are connected to consequences, and when it continues over time as the system evolves. For brand new learners, the key takeaway is that impressive outputs are not proof, and average scores are not the whole story. The only reliable way to trust an AI system is to validate it with evidence that reflects reality, then keep revalidating as reality changes.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.